AP Calculus AB, we're in Note Section 5.5, examining net and total distance. This is video 3 of 3. We're looking at some examples, putting what we have learned in the previous videos into practice. The position of a particle is given by the function p of t, where p is measured in centimeters. Find the net and total distance the particle travels from 1.5 seconds to 4 seconds. Now, to find the net distance, that's pretty simple. Notice this says this is a calculator problem. We're going to take the absolute value of p, the position at the starting position, minus the position of the particle at the ending time. And if you were to put into your calculator, two times 1.5 cubed minus 6 times 1.5 squared plus 8 times 1.5 minus putting 4 in for those. And you would end up with this net distance of being 58.75 centimeters. Our total distance, much more complicated, because every time this particle changes direction, we need to have another absolute value here. So, in order for us to figure this out, we got to figure out, does the particle change direction? Specifically, does it change direction on the interval 1.5 to 4? That's what we got to figure out. To do that, we got to figure out if the velocity changes signs. So we're going to have to make a Sine diagram for velocity. So the velocity can be found by taking the derivative of the position function, which is just going to be 6t squared minus 12t plus 8. When the derivative is equal to 0, that's when the velocity could change direction. I'm going to factor a 6 out of this. Well, let me stop here for a second. I can't factor a 6 out of this 8. If I were to factor a 2 out of each of these terms, I would get 3t squared minus 6t plus 4. And I would need to be able to produce a factoring scenario where we took these first two terms and multiplied them together, and we need two terms that are able to do that, and the same two terms add to get the middle term. Long story short, this does not factor. So I'm going to complete the square, which is something that we have not done much of this year. So I am factoring a 6 out of those two terms only, and I am leaving the 8 alone. Just moving it to the outside of the parentheses. To complete the square, I'm going to take half of the coefficient of t, so half of that's -1. Then I'm going to add it, take half of that and then square it. Half of -2 is -1, squaring it, it's +1. I can't just add 1 to the equation. If I add 1, I have to also subtract 1 to counteract it. Now keep in mind, although this looks like I'm adding 1, I'm actually not. I'm adding a 6 times 1, because that gets distributed. So to counteract it, I have to subtract a 6. If I add a 6 and subtract a 6, it doesn't change the value of what's happening, it just changes how this looks. We just completed the square. Once the square is completed, this is a perfect square trinomial, which factors into a t minus 1 quantity squared. Bring down the 0, the equals, the 6 times. A +8 and a -6 is a +2. Now to get t by itself, because I want to figure out when this is equal to 0, so I can make a sine diagram, I'm going to subtract 2 from both sides, divide both sides by 6, and I have an issue now. Because when I square root both sides, I'm going to end up square rooting a negative number, which means this is going to be imaginary. Which means the velocity never equals 0 on the interval from 1.5 to 4. Since the velocity never equals 0, this particle could not be changing direction any place on this interval. So I would say this has no solution. And then I could make the following conclusion. Does the particle change direction? No, the particle does not change direction. So there are two things we're supposed to find. Find the net and total distance. We found net already. According to what we wrote up here, the net distance could equal the total distance as long as the particle never changed direction, and this particle did not. So we could say the total distance is 58.75 centimeters because the particle never changes direction. On the interval of 1.5 to 4. All right, very good. First example, let's check out a second example. This one also is going to require a calculator. The position of a particle is given by a function measured in feet. Find the total and net distance of the particles. So very similar to what we just did, very similar function as well. To find the net distance, take the absolute value of the position at the beginning time minus the position at the ending time. If you were to evaluate this with your calculator, you would find that it's 9.367 feet. That is the net distance traveled. Is the total distance going to be the same as that? It could be if this thing never changes direction. Well, let's figure that out. So we want to ask the same question. Does the particle change direction on 0.5 to 1.5? So to figure this out, we got to find the velocity, which is the derivative of the position. The derivative of e to the 2t is just e to the 2t times the derivative of the exponent. So that's going to be 2e to the 2t. Derivative of minus 8t is going to be minus 8. When the velocity is equal to 0, that's when this is going to change direction. I'm going to factor a 2 out. I'm going to set each factor equal to 0. 0 equals 2. That doesn't make any sense. E to the 2t minus 4 equals 0. How do I solve this? e to the 2t equals 4. This is an exponential form. If I change it to logarithmic form, I'm going to have natural log of 4 equals 2t. This is exponential form. This is log form. If you don't like that, another way to look at it is I natural log both sides. If you natural log this side, natural log with the same base e becomes 2t. Natural log of this is natural log of 4. To get t by itself, I multiply both sides by a half, and I'm going to get a half of natural log of 4 is t. If you put that in your calculator, this is approximately 693 thousandths. That is between these two. So this thing does change direction, possibly. At the very least, it stops for a moment. So just to determine for sure if it's changing direction, we're going to make a sine diagram. Since my sine diagram has a beginning and end, I'm not going to put arrows on it. The beginning is half a second and the end is 1.5 seconds. And then we found someplace in here, this is equal to 0. If you were to pick a test point in each of these intervals, and you were to plug them in to the velocity function, for example, if you put in 0.6 into this, put it in your calculator, you would find that this interval is negative. How do we interpret that? We interpret that if the velocity is negative, this particle is moving left. If you put a test point in like 1 into this, you're going to find that this is right in this interval. And how do we interpret that? The particle is moving to the right. Therefore, this little fella has changed directions. So I'm just going to write that down formally. Let me answer this question that I posed up here. The particle does change direction. Since the particle changes direction, the net distance could not equal the total distance. So for us to find the total distance, it's kind of a pain. We got to take the beginning position, which is the position at time half a second, subtract from that where this first changed direction, which is at time 0.693, find that absolute value, and then add to that where this position first changed direction, subtracted from the time when the position, not the time, but the position of the particle at the time when this stopped, which is 1.5. The calculator should give you 9.894 feet, which is pretty similar to the net distance, and yet different. Last one is a non-calculator. The position of a particle is given by this function where p is measured in feet. Find the net and total distance traveled at these times. Well, let's do net first because it's easier. Hey, what? Maybe this is a calculator problem. Let's assume this is also a calculator problem. Net distance is the absolute value of p at the starting time minus p at the ending time. Using a calculator, you would find that this is 989 thousandths of a foot. Does this thing change direction? To determine if it changes direction, we need to take the velocity Set it equal to 0. The velocity is the derivative of the position. Derivative of t is 1. Derivative of 2 sine of t is 2 cosine of t. Set this equal to 0, and we solve this, and this is going to be good practice for us to solve a problem in which we're using trigonometry. Subtract 1 from both sides, divide both sides by 2, and I want to know, when is the cosine function equal to negative 1/2? If you're great with a unit circle, you probably know the answer instantly. I'm not great with a unit circle. I'm just going to draw this. I know that cosine is x over r, so my x value is negative 1, so I'm going to the left, and my r value is 2. That means that this triangle that I'm drawing could be in quadrant 2, or it could be in quadrant 3. Two possible answers. I have to know my special right triangles. If a leg is 1 and the hypotenuse is twice that, that must mean that I'm dealing with a 30, 60, 90, and in radians, that would make this pi over 3, makes the small angle pi over 6. Whoops. So 30 degrees, opposite that's the smallest side, opposite pi over 3. I don't have to know this for this problem, though that would be the square root of 3. And this one would be negative square root of 3. So I want this angle here, which is going to be 2 pi over 3. And I also want this angle here, which is going to be 4 pi over 3. Now, do either of those fall in the interval? Pi over 6, yes. 5 pi over 4, no. So from this, I'm saying t is 2 pi over 3, and t is 4 pi over 3. However, 4 pi over 3 does not fit in the interval. So it does change direction. Or at least I know that it is equal to 0. It's possible that it comes and it touches the x-axis and returns from where it came. So I need to make a Sine diagram. Beginning, end, and where it's equal to 0 is at 2 pi over 3. This is the velocity. If I pick a test point here, like if I choose t equals pi here, and let's say over here I choose t is pi over 2. If I put pi over 2 into this, cosine of pi over 2 is 0. That's going to make this positive. 0 plus 1 is positive. If I put pi into this, cosine of pi is negative. Specifically, it's going to be negative 1. This is going to be 1 minus 2, because 2 times negative 1 is negative 2. That's going to make this negative. So my conclusion is this little fella is changing direction. So to find the total distance, I take the position at the starting time minus the position at the time when it changes direction, take their absolute values, add to that the absolute value of the position at the changing direction time minus the position of the particle when it stops, at least when this time period ends. And I would find that this is about 3.617 feet, which is quite a bit different than the net distance. That concludes the notes for this section. Hopefully it made some sense. Net distance is a lot simpler than total distance. That's the big takeaway for this lazy guy.